this is Dr. Hanaa Assil, and this is Unit 5 of October 2024 in the Pearson Edexcel International A-Level Chemistry. So let's take a look at the questions and discuss the answers. So the first question in this paper was, what is the electronic configuration of the chromium atom? Of course, we go to the periodic table and we check what is the atomic number of chromium. You find that the atomic number of chromium is 24. Now, how are the 24 electrons distributed? You should remember that we said we distributed 1s2, 2s2, 2p6, 3s2, 3p6, and then we put into the 4s, so we're supposed to say 4s2, and we're left with 4 electrons. So actually chromium atom should be 4s2 3d4, but we said that means that the 3d needs just one more electron to be half filled. So actually we take one electron of the 4s, so that now it is 4s1 3d5. That in that case both the 4s and the 3d are half filled, and you should know that in the shorthand method, the 1s2, 2s2, 2p6, 3s2, 3p6, this is the electron configuration of argon, which is 18. So the chromium atom is argon with 3d5, 4s1. Which ion shows the typical property of transition metals by forming colored complexes? We know that transition metals form colored complexes, and the question is, which of these is colored? So we know that due to the presence of ligands in the transition metal complexes, the d orbitals split. Instead of being all of the same energy, all 5 d orbitals should be of the same energy, but when we have complexes, the presence of the ligands causes the d orbitals to split, so that 2 of them have higher energy than the other 3. Now, if an ion has incomplete d sublevel, that means some of the d orbitals are not completely filled, then any electron in the lower energy level can absorb energy, jump to the higher d orbitals, and the rest of the light goes through and is transmitted to give a color. Now, that means in order for the complex to be colored, we must have basically incomplete d sublevel. So let's take a look at each of these. Copper is what? Copper is originally atomic number 29. So originally it is 4s1 3d10. So if we say copper plus 1, that means we're going to lose which electron? We said we lose first from the 4s. So copper 1 will lose the electron in the 4s1, and that means my 3d is still completely filled. So that will not be colored. Nickel 2 plus, nickel is 28. It's 4s2 3d. 8. Now, if we say nickel 2 plus, that means I have lost the 2 electrons in the 4s. I still have incomplete 3d sublevel, so that means nickel 2 plus is colored. So that's supposed to be our answer. Let's check the others. Scandium is 21, 4s2 3d1, and that means if I say scandium 3 plus, I have lost the 2 electrons in the 4s and that electron in the 3d. So scandium 3 plus actually has an empty d sublevel, so no electrons to absorb energy and jump to a higher energy level. So scandium 3 plus is not colored. Zinc 2 plus, zinc is 30, 4s2 3d10. when we lose 2 electrons, we're going to lose the 2 electrons that are on the 4s, and that means the 3d is completely filled. Again, we said if the 3d sublevel is completely filled or completely empty, no color. It is colored only if the D sublevel is incomplete. So the only one here that's colored is nickel 2+. The formula of a chromium compound is this. The molar mass of the compound, that means the MR of all of this, is 230.5. And we are asked to get what is the percentage by mass of chlorine in the what? In the complex ion. Which part is the complex ion? This part is the complex ion. The complex ion will not include that chloride that is alone out there. So we are looking at the complex ion, at this. So we're going to calculate the MR of this. So the MR of this is the 230.5 minus that chlorine that's outside. So it's 195. In the complex, I have 2 chlorines, so that's 2 times the mass number of chlorine times 100. That would give me the percent mass of chlorine in the ion, not in the complete compound. Most of the mistakes were they looked at the 230.5, but we're not talking about the whole compound. We're talking about that complex ion without that extra chloride that's outside. The reaction between peroxodisulfate and iodide ions is shown. The reaction has a high activation energy but is catalyzed by ion 2. What is the best explanation for the high activation energy of this reaction? Remember that we said this is a reaction that is catalyzed by ion 2. So we said all of these are solutions and the catalyst is a solution. So this is an example of homogeneous catalysis. And we said that reaction originally is very slow. Why is it very slow? Because both reactants are negatively charged, so they will repel each other. So they're not likely to come together and react. And that is why we put ion 2+, and you are required to know these equations, that if I put ion 2+, it reacts first with the S2O8 2- and becomes ion 3+, and then the ion 3+ reacts with the other reactant and becomes or returns back to its original state of ion 2+. So why does this reaction have a high activation energy? Why is it slow? Because both reactants are negatively charged. Okay, so which property of iron 2 ions enables them to function as a catalyst for this reaction? Why is it that we can use iron 2 as a catalyst? Remember that what happens is the iron 2 changes to iron 3, so it is oxidized to iron 3, and then it is reduced back to iron 2. So we use it because it can be easily oxidized and then reduced. Chromium 3 hydroxide is amphoteric. This means that chromium 3 hydroxide dissolves in what? Remember, what do we mean by amphoteric? You should remember that amphoteric substance is one that can act as both acid and base. That means you put it in acid, it will react as a base. You put it in base, it can react as acid, and that means it can dissolve in both acid and alkali. Naphthalene is an aromatic molecule with 2 aromatic rings. Remember, we said the word aromatic means a benzene ring in which you have delocalized electrons in the ring. So naphthalene has 2 rings. It can be nitrated at position 1. So we know, just as benzene, we can add nitric acid and put an NO2 on it. in an experiment, a 2-gram sample of naphthalene was nitrated and produced 2.57 grams of the product. What is the percentage yield of this product? Again, to calculate percentage yield, we should first calculate the theoretical yield, how much should they have obtained, and then relate it to what they actually got. So if we're starting with 2 grams, we need to calculate what? We need to calculate number of moles, mass over molecular mass. We're given the MR. So this is the number of moles of naphthalene we're starting with. The equation obviously shows that the number of moles of naphthalene is the same as the number of moles of the product. And that means now I have the number of moles of product. I can calculate the mass that should be obtained. The theoretical mass is number of moles times its MR. So we should get 2.7 grams. They actually got 2.57. That is about 95.1% of the theoretical mass. Calculated the percentage yield of the reaction to be greater than 100%. So he thought that what he got was much more than what he should get. So what is the most likely explanation for this? If we look at these choices, we're saying that he got more of the product. So if we say there was unreacted naphthalene, if there was unreacted naphthalene, he should get less of product. The naphthalene was impure, he should get less of the product, not more. If the sample of the product was damp, yes. If he did not dry the product properly before weighing, then the mass that he gets of the product will be too high. Again, if we choose D, other isomers were produced. Well, if other isomers were produced, then he should get less, not more than what he should get. So the only choice that would give him more than he should get is if what he weighed at the end was damp. This question is about the azo dye, which has this structure. In the production of this compound, phenylamine is first reacted with nitrous acid. Which equation shows the formation of nitrous acid from sodium nitrite? Remember we said, if I want to add a diazonium salt onto the benzene ring, we should react the phenylamine with nitrous acid. But we said nitrous acid alone is very unstable, so we do not add to the reaction nitrous acid. We actually add a mixture of sodium nitrite and HCl, so that the nitrous acid is produced within the reaction. And we said, of course, this needs a temperature below 10 degrees Celsius because the diazonium product, diazonium salt produced, is unstable at high temperatures. So to make the nitrous acid, we react what? We react sodium nitrite with HCl to give the nitrous. Again, nitrous acid is HNO2, not HNO3, and what we start with is sodium nitrite, so it's NaNO2, not NO3. The reaction of phenylamine with nitrous acid produces the diazonium salt. What is the structure of the diazonium ion? Remember we said we started with phenylamine, we're putting sodium nitrite and HCl. What we get is a diazonium salt. The diazonium salt is something that has N triple bond N, and that means that N that is attached to the benzene ring has 4 bonds instead of 3, so it has an extra positive charge. So remember, the positive charge is placed on the nitrogen that's attached to the benzene, not the nitrogen at the end. Which reactant is required for the coupling reaction with the benzene diazonium salt to form that product? So the benzene diazonium salt, I want to react it with something to give that product. Now, what is extra in that product? That is the part that's extra. So that is the part that I'm going to react with. And remember, the diazonium salt reacts directly with the benzene ring. It does not need to displace something from the benzene ring. So we shouldn't have an OH on the benzene or an NH2 on the benzene or even a diazonium on the benzene. So all the other choices are wrong. We react the diazonium salt directly to the benzene ring. The amino acid serine has the structure shown. What is the IUPAC name for this compound? To determine the IUPAC name, we look at the longest chain. Where is the longest chain? The 3 carbons are the longest chain. So this is prop not S. We have 3 carbons all attached to in a chain, so that is propanoic acid. And then on the propanoic acid we have an amine and a hydroxy. I'm going to remind you that when we have 2 substituents, we arrange them alphabetically. So we mention the amino part first and then the hydroxy, and we count from the side of the carboxylic acid. So the carbon of the carboxylic acid is carbon number 1, and that means the amino is on carbon number 2 and the hydroxy is on carbon number 3. Which is the organic product of the reaction between serine and sodium hydroxide? Serine is an amino acid, so that he gave me this structure of serine. It's an amino acid. So he's saying we're going to put this amino acid in a base, in sodium hydroxide. What is the appearance of an amino acid or the state of an amino acid in a base? At high pH, we said what happens is the acid part is a salt, a sodium salt in the acid part, and the amine part remains the same. It doesn't have an extra hydrogen. Remember, when you put it into an acid, then you have the acid part is a C double bond OH and the amine part is an NH3 plus. Remember that an amino acid in neutral pH exists in the form of a Zwitter ion, where the acid part is COO minus and the amine part is NH3 plus. Now, when we put it, as we said here, in sodium hydroxide, that means high pH. That means the acid part is the sodium salt, so that is COO minus, and the amine is as it is, NH2. Now, if I put the amino acid in acid or low pH, then the amine part is NH3 plus, and the acidic part is COO. The cumene process is the main industrial method for making phenol. The overall equation for this process is shown. What is the atom economy by mass of this process for making phenol? So we're trying to make phenol. We want to calculate the percent atom economy. You should remember what is the percent atom economy. It is the molar mass of the desired product over the sum of the molar masses of all products times 100. So we want the MR of phenol, so that is 94, over the total MR of both products times 100. That gives the atom economy. I want to remind you that if we had any coefficients in front of these products, we would include the coefficients. So if the reaction says it gives 2 of phenol, I would multiply the MR of phenol by 2 and so on. Okay, so that is the percent atom economy. Now this question says an aromatic compound, again I'm going to remind you, aromatic compound means a benzene ring with delocalized electrons. This compound has a 10 carbon ring and it has the structure evidence for aromaticity of this compound is that the carbon-carbon double bonds in the 10-carbon ring, we said, how do we prove that the double bonds are actually delocalized over the carbon atoms, not individual single and double bonds? This was because all the bonds have similar lengths. If they were single and double and single and double, the single bonds should be longer in length than. So remember that one of the evidence that benzene is aromatic or it has delocalized electrons is the fact that it doesn't have different lengths, because if they have alternating single and double bonds, then the single bonds should be much longer, or at least longer than the double bond. The aromaticity is due to the formation of pi bonds as a result of overlap of which orbitals. Remember that in the benzene ring we said the electrons that are delocalized are the electrons in the p orbital, so that they are delocalized over all the carbon atoms, and that forms the cloud of delocalized pi system. The polymer nylon 610 is made from, and pay attention to the question, it says a 6-carbon diamine and a 10-carbon dicarboxylic acid. So what is the repeat unit? So we're looking for something in which the two ends have 6 carbons between them, and the two acid parts, the two carbonyls, have a total of 10 carbons. So the only one that applies to that is this one. The others have different numbers of carbons in the two units. Here the diamine has 6 carbons in addition to the 2 nitrogens, and the diacid is the one that had the C double bond O. It has a total of 10 carbon atoms. Car exhaust gases react on the surface of a catalytic converter. Which interactions could not occur between the gases and the catalytic converter in this process? Remember, a catalytic converter is placed on the car exhaust in order to change the harmful gases that are emitted from the engine or from the burning of the fuel into safer gases. Now, how does the catalytic converter work? You should remember that the reactants are adsorbed on the surface of the catalyst. This weakens the bonds. Reaction occurs, and then desorption of products from the surface occurs. So what we do not have is we do not have hydrogen bonds happening between the gases and the converter. We don't even have hydrogens bonded to electronegative elements. Which pair of equations shows the most likely mechanism for vanadium oxide acting as a catalyst in the contact process? Again, remember, you need to know what's the contact process. That is the reaction of SO2 with O2 to give SO3. And we said we use vanadium 5 oxide as a catalyst, and that is because the V2O5 reacts first with the SO2 to form the V2O4, and then the V2O4 reacts with the oxygen to be returned back to its original state. The formation of carbon dioxide from the reaction between manganate ions and ethane diuate ion is autocatalyzed by manganese ions. Which graph for the complete reaction shows the autocatalysis of this reaction by the manganese 2 ions? Okay, we said this is an example of autocatalysis in which the reactants, again here, the reactants are both negatively charged, so they're less likely to collide because they will repel each other. So at the beginning, the reaction is slow. But then, as the manganese 2 plus is being formed, the presence of the manganese 2 plus acts as a catalyst for this reaction, so the reaction speeds up. And then at some point all the reactants have been used up, so the reaction will finish. So which graph shows that? Of course, the graph in which the reaction is slow at the beginning, so you cannot choose A or B, and then it speeds up, but then it eventually stops or slows down because the reactants have been used up. This question is about butylamine. The boiling temperature of butylamine is 78 degrees Celsius, which is much higher than alkanes of similar molar mass. Butylamine is miscible with what? Draw a label diagram to show one of the intermolecular interactions between a butylamine molecule and a molecule of water, and we need to include lone pairs and dipoles. So butylamine is something that has a nitrogen with a lone pair of electrons. So we can have a hydrogen bond between the lone pair of electrons on the nitrogen and the hydrogen of the water, or actually you could draw also between the hydrogen of the amine and the oxygen of the water. Important thing, the hydrogen bond is a linear bond, bond angle 180. The nitrogen, of course, is slightly negative, hydrogen slightly positive, and oxygen slightly negative. Butylamine has a fishy ammonia-like smell. The exposure limit or safety level in the atmosphere for butylamine is 15 milligram per meter cubed. Calculate the maximum number of butylamine molecules that are allowed per cubic meter. So we want to know this 15 milligram in a cubic meter is how many molecules. To know the number of molecules, of course, we first need to get number of moles. So the MR of the molecule is 73. Number of moles is the mass over the molecular mass. Please remember again, mass has to be in grams. So he gives me 15 milligram. That's 15 times 10 to the minus 3 or 0.015 over the MR. That's the number of moles. How do we get number of molecules? We multiply that by Avogadro constant, and this gives the number of molecules. Butylamine reacts with ethanoyl chloride to form N-butyl ethanamide. Write an equation for this reaction using displayed formula. So how do we draw butylamine plus ethanoyl chloride to give the product? Of course, you should know that the product is the nitrogen replacing the Cl to form an amide linkage, plus the hydrogen and the Cl that were removed. The other product is HCl. Please remember, if he's asking for displayed, then we should give displayed. Explain why butylamine is a stronger base than ammonia. Remember that we said butylamine is something that has nitrogen with a lone pair of electrons. Now, why is it stronger than ammonia? Both of them have lone pairs that can be used to make a dative bond to H+. But we said that the presence of an alkyl group, like butyl group, we say it is electron donating. That means that the nitrogen, the lone pair of electrons on the nitrogen, is more available to bond with the H+ ion or to form a dative bond with the H+ ion than the lone pair of electrons on ammonia. Iron is generally prescribed when a person is suffering from anemia. Many people find it easier to take medicine in liquid form rather than solid tablets. An iron solution advertised for this purpose contains iron as iron 2+. An adult is advised to take 90 milligram of iron daily. 25 centimeter cube sample of that solution that we have. So this is the original solution, 25 centimeter cubed. This was made up to 100 using sulfuric acid and deionized water, and then 25 of that diluted solution was titrated with potassium permanganate. Now the reaction is shown. Calculate the volume of the original solution required to obtain a 90 milligram dose of iron. So we had that original 25 centimeter cubed of the iron 2 solution. How much should I take of it in order to take 90 milligram of iron? Well, in order to do that, the first thing is we have the titration with the potassium permanganate, concentration and volume, get the number of moles of manganate, concentration times volume. Now look at the equation, relate the number of moles to the number of moles of iron 2. Well, obviously number of moles of iron 2 should be 5 times of that. But this is the number of moles of iron 2 in the 25 centimeter cube that we titrated. Now that was taken from 100 centimeter cubed of diluted solution. So you need to get how much iron 2 was in that total 100. So you multiply, instead of 25 I want in 100, so multiply by 4. And that is the number of moles that were present in the original 25 centimeter cubed. Now we want a mass of 90 milligrams. So the mass of the total mass of the iron 2 plus in that 25 centimeter cube solution is, of course, number of moles times the MR of iron. So that's 0.226. That means all the 25 centimeter cubed original solution of iron 2 had 0.226 grams. Now I want to know how much we should take in order to have 90 milligrams. So the 25 centimeter cubed had 0.226. How much of that solution will have 0.09 grams? Of course, you're comparing grams, or you could compare both of them, milligrams. And that means that the volume of the original solution needed is about 10 centimeter cubed. This question is about electrochemical cells, and the first thing is, describe how you would carry out an experiment to determine the standard electrode potential of a cobalt 2 plus half cell. Now, how do we determine the standard electrode potential of any cell? You should remember that we relate it to a hydrogen half cell, the standard hydrogen electrode. So what you're trying to describe is, how do you set this up and what do you do to get the standard electrode potential of cobalt? So, of course, we need to connect this to a hydrogen half cell. So what we do first is we have this hydrogen electrode with hydrogen gas, and you need all the conditions. 1 atmospheric pressure, HCl, it should be dipped into a solution of HCl of concentration 1 mole per decimeter cubed, 298 Kelvin. We need a platinum electrode covered with platinum black that is in contact with the hydrogen gas. So that is the standard hydrogen electrode. Then we need to connect this to the other half cell using a salt bridge. Remember, the salt bridge is a saturated solution of potassium nitrate. Then we have that other half cell. We need cobalt in cobalt 2 plus solution. So you have to be specific. The cobalt as a metal will be the electrode. The solution will be a solution of what? Remember that all nitrates are soluble. So if I want a soluble salt of cobalt, you can say, or the best bet would be to say cobalt nitrate solution. Remember that all the solutions have to be at a concentration of 1 mole per decimeter cubed, all of this is connected to a voltmeter, and the electrode potential indicated by the voltmeter is the electrode potential of the cobalt half cell. Remember that we give the hydrogen electrode an E of 0. So whatever reading we have on the voltmeter, that's the reading for the cobalt half cell. Acidified potassium dichromate is an oxidizing agent. The acid used is sulfuric acid. Remember, if we want to oxidize something, we say we use acidified potassium dichromate, that is potassium dichromate with concentrated sulfuric acid, not concentrated hydrochloric. And the question is, explain why concentrated hydrochloric should not be used to acidify the potassium dichromate. Well, these electrode potentials for potassium dichromate, that's the first one we're using. But the second one, if we're going to use dichromate as an oxidizing agent, then the chlorine should be the one that is oxidized. Chloride has to be oxidized. So we're inverting that second equation to make it an oxidation reaction, loss of electrons. And that means we invert the E cell. And that means if we add up the total of the E cell, it is almost 0. It's minus 0.03. That is very near to 0. So this should not react. But what if I have concentrated hydrochloric acid? That means I'm adding a lot of H plus and I'm adding a lot of Cl minus. And that means the E cell originally is negative, so it should not work. But when we use concentrated HCl, then the presence of the H plus will cause that first equation, the equilibrium shifts to the right, and also the second equation also shifts to the right, and that means the E of the cell goes above 0. So if it is very near to 0, remember, using concentrated solutions would force the reactions to go more forward, so it would increase the E cell, so it will go above 0 and become feasible. In addition to the fact that when that happens, then we're forming chlorine gas, and chlorine gas is toxic. The cell diagram for an electrochemical cell is shown. Write the reduction half equation for this cell. So, remember that when we write the cell diagram, the part on the left is the part where we have oxidation. The part on the right of the salt bridge, that is the part that has the reduction. We are already given the reactants, so the reactants are VO2 plus 2H plus to give VO with 2 positives plus water. We are told that state symbols are not required. This is reduction, that means gain of electron. Check to see if it is balanced as it is. Well, yes, it is balanced, so that is our equation. The direct methanol fuel cell uses methanol and oxygen to generate electricity. When the cell operates, methanol reacts with water at one electrode to produce carbon dioxide and hydrogen ions. At the other electrode, oxygen reacts with hydrogen ions to form water. And we are told to write the oxidation half equation for this fuel cell. So, where do we have the oxidation? That is the part that says methanol reacts with water, and we are told it produces carbon dioxide and H plus, and then we check, is this oxidation? This is oxidation, that means we're losing electrons, so we have electrons after the arrow, and then you need to balance so that the atoms and the charges are balanced. So the carbon is balanced, 4 and 2, 6, so that's 6H plus, and we have 2 oxygens, and now I have 6H plus. That means I need 6 electrons, and now it is balanced. Write the overall equation for this fuel cell. Well, we wrote the equation for that first one, and then we were told that at the other electrode, oxygen reacts with H plus to form water. Again, that means this is the reduction, so we gain electrons, and we balance them so that number of hydrogens is correct, number of oxygens is correct, and the charges are balanced. So these are the 2 half equations. Now we are required to write the overall. We said in order to add up 2 half equations, the number of electrons must be the same. So what should we do? If we multiply the one on top with 2 and the one below with 3, this is what we get. So now the number of electrons are the same. Now, if we have the same thing on both sides of the arrow, they cancel. So that means 12H plus cancels with 12H plus. We also have water on both sides of the arrow. We cancel them and write what is left. So the overall equation is the part of the methanol plus oxygen, and the water, we have 2 before the arrow, 6 after the arrow. That means we have a net amount of water that is 4 water with the 2 CO2 that is formed. This is the overall equation. The reduction half cell in this cell has a standard electrode potential of plus 1.23. When the solution concentration changes, remember that the E note that is given, this is for the cell under standard conditions. That means concentration of 1 mole per decimeter cubed, temperature 298, pressure 180 m, and so on. Now, when the solution concentration changes, so we're no longer under standard conditions, he says the E cell now is plus 1.20. And we use this equation in order to determine the X. So what is the concentration of the solution? We put in the numbers into that equation, and what we're trying to get is X. You should be able to solve this equation for X. So the E alone is the plus 1.2. The E note is the 1.23 plus this number times natural log of X. So you can get the natural log of X, that comes out to this number, then inverse of the natural log, that gives you X. You should be able to do that with your calculator. This question is about colored transition metal complex ions. The iron 2 plus complex is green, iron 3 plus complex is yellow. Explain why the iron complex is colored. You need to be able to explain why transition metal complexes are colored. Remember that we said the 5d orbitals originally are the same energy, but the introduction of ligands around the transition metal causes the d orbitals to split so that 2 of them have higher energy than the other 3. So the d orbitals are repelled by the bonding electrons with the ligand. The d orbitals split so that 2 are at a slightly higher energy than the other 3 d orbitals. Now, when light shines on the solution, an electron absorbs a certain amount of energy equal to the energy difference between the 2 levels. The electron absorbs that energy, jumps to a higher d orbital, and the rest of the visible spectrum is transmitted, and this is observed as a color. Remember that we said if we're asked why do they have different colors, we say because different compounds have different energy gaps. So that difference in energy between the 2 sets of orbitals is different for different compounds, so the amount of energy absorbed by the electron in order to jump to a higher energy level is different from one compound to the other, and that is why the light that is transmitted gives different colors. Explain, and that is the question, explain why the two iron complex ions are different in color. They have different colors because different energy gaps between the orbitals, so the electron absorbs different wavelengths of light to jump to the higher energy d orbitals, so different colors are seen. The thiocyanate SCN- forms a blood red colored complex ion with iron 3. The dot and cross diagram for the thiocyanate ion can be drawn in more than one way. For example, the negative charge can be on the nitrogen atom, as shown. So this is given to us. Now complete the alternative dot and cross diagram of the thiocyanate ion where the negative charge is on the sulfur. So we are required to use the dark dot for nitrogen, X for carbon, asterisks for the sulfur electrons, and a triangle for the extra electron that forms the negative charge. So how do we distribute the electrons? Well, nitrogen, if we start on the right, nitrogen has 5 electrons, it needs 3 more, so it will have a triple bond with the carbon, sharing 3 pairs of electrons, and it still has a lone pair of electron alone. Now the carbon needs a total of 4 electrons, so it forms 3 bonds with the nitrogen, 1 bond with the sulfur, and the sulfur is the one now that has the extra electron that is drawn as a triangle. 12.8 centimeter cubed of this concentration of iron 3 solution reacted with this amount of ammonium thiocyanate to form a complex ion. Deduce the formula of the octahedral complex ion that iron 3 forms with thiocyanate. So basically we're told it's going to be octahedral, and that means the iron 3 will bond to 6 ligands. How many of them will be thiocyanate? That's what we're looking for. So based on what we're told, I can get the number of moles of iron 3, concentration times volume, and I can get the number of moles of the thiocyanate, and I find that they're the same number of moles. That means the ratio of the thiocyanate to the iron 3 is 1 to 1. That means my iron 3 complex has only 1 thiocyanate, but it is octahedral. That means the other 5 ligands must be the water ligands. So this is the formula of the octahedral complex ion. Colorimetry was used to determine the concentration of a solution of copper 2 sulfate. 6 solutions of copper sulfate of known concentration were prepared. Their absorbance at a wavelength, a certain wavelength, was measured. The results are shown. We are required to plot this information into a graph. So, of course, the graph paper first, we label. The x-axis will be the concentration and the units. Don't forget to put the units. And the y-axis will be the absorbance at 635 nanometers. And we divide the graph so that we use as much of the graph paper as possible. Plot the points. This is obviously a straight line going through the origin. 50 centimeter cubed of a solution of copper sulfate of unknown concentration was pipetted into a 250 centimeter cubed volumetric flask, and the volume made up to the mark with deionized water. The absorbance at a wavelength of 635 nanometer for this diluted solution was 0.72. determine the concentration of the original copper sulfate solution, you must show you're working on the graph. So we have a graph of absorbance at 635 nanometer, and we are told that the absorbance for this solution is 0.72. So where is 0.72? We go down to the concentration. It has a concentration of 0.26 mole per decimeter cubed, but that is the diluted solution. So that is the concentration of the 250 centimeter cubed of volumetric flask. So the number of moles is the concentration times the volume. So that is the number of moles in the 250. Now we want the concentration of the original 50 centimeter cubed. It's the same number of moles that we put in 250, but we're going to divide it by the volume of 50 centimeter cubed, and the original concentration comes out to 1.3 mole per decimeter cubed. Give one possible reason why any concentrations of copper sulfate determined from the graph of values over 0.5 mole per decimeter cubed are uncertain. Now, when we look at the graph, we have that the graph is a straight line up to 0.5. Can we use the graph for concentrations higher than 0.5? Well, not really, because we're not sure what the graph looks like after 0.5. It may not be a straight line, so just extrapolating the line may not give the correct concentration. The complex ion formed from cobalt 3 ions and ethane 1,2-diamine is a yellow-orange color. The equation for the formation of this complex is shown. Give a reason by referring to the equation why the formation of the diamine complex from the aqueous complex ion is thermodynamically favored. Why is this reaction feasible? We said there are many things that make a reaction feasible, but just looking at the equation, you can tell that the number of moles is increasing. So we're starting with 4 moles of reactants and we're given 7 moles of products. That means the delta S is, or the entropy change for the system, is positive, and therefore the reaction is feasible. Explain by reference to the structure of ethane 1,2-diamine why it is a bidentate ligand. Now this is ethane 1,2-diamine. Why is it a bidentate ligand? Of course, that is because it has 2 nitrogen atoms at its ends. Each of them has a lone pair of electrons that can form a dative bond with a central metal ion, and that means that this ligand can form 2 dative bonds to the central metal atom and therefore ion, and that's why we say it is bidentate. Explain how the H-NH bond angles would be expected to change in the ethane 1,2-diamine when the complex ion is formed. So we're starting with ethane 1,2-diamine. This is the structure, and that means I have nitrogen with 3 bonding pairs of electrons and a lone pair of electrons on the central metal, on the central atom, and therefore we said this kind of structure would be pyramidal with a bond angle of 107. So that is in the initial ethane 1,2-diamine. But when it bonds to form a complex, what is happening now is the nitrogen now has 4 bonding pairs of electrons, no lone pair of electrons on the central atom. So now it is tetrahedral with a bond angle of 109.5. Raspberry ketone over 200 different compounds contribute to the smell of raspberries, including the one known as raspberry ketone. This is also found in other fruits such as cranberries, blackberries. It can be extracted from fruit, but it is present in a very low percentage, and so it is prepared industrially by a variety of methods. The two-step method shown gives a 99% yield. So this is the synthesis we're talking about. Two other compounds which contribute to the characteristic smell of raspberries are these shown, the alpha ionone and the beta ionone. And the first question says, give the empirical formula of this compound. In order to get the empirical formula, we get the molecular formula first. So I always look at where are the carbons, where are the hydrogens, total number of carbons, hydrogens, and oxygens. That is the molecular formula. Now, to make to get the empirical formula, we said we simplify the ratios. It is the formula showing the simplest ratios. So here the carbon, hydrogen, oxygen 10 to 12 to 2. If you simplify that, the empirical formula is C5H6O. Raspberry ketone can be synthesized in the laboratory from phenol using a Friedel-Crafts reaction. The overall reaction is shown. Now, the first question is, draw the mechanism for this reaction using appropriate curly arrows. Include equations showing the formation of the electrophile and regeneration of the catalyst. Of course, if we have this Friedel-Crafts reaction, we should know that the first step is, first of all, we use aluminum chloride catalyst, and that is because this is what helps to form the electrophile. The bond going to the chlorine is used to make a bond to the aluminum chloride. So now we end up with aluminum AlCl4 with a minus, and the electrophile is now a positively charged carbon. Now, this can be attacked by the benzene ring. So from the benzene ring to that positively charged carbon, we have an intermediate in which the ring has a partial positive charge. Remember that that incomplete circle inside the benzene ring has to be opened at the carbon at which we added the incoming reactant, and then the AlCl4 will use its extra chlorine to remove that extra hydrogen and give its electrons to the benzene ring so that we get the product plus HCl and the catalyst is regenerated. Give a reason why the yield of the raspberry ketone by this method is not high. So we're trying to put this incoming chain at a certain position, but this may not be the only product that we get, so other products may be obtained in which substitution happens at different positions on the ring of the other carbons, and that means we have other side products being formed. Raspberry ketone can also be synthesized in the laboratory using a Grignard reagent via a multi-step process. The overall reaction is shown, and we are required to devise the multi-step synthesis. Remember, he wants us to use the Grignard reagent. Give the reagents and conditions for each step, including the formation of the Grignard reagent and the structures of the intermediates. So we're starting with that compound on the left, and we're trying to make our ketone product. So what should we do? We're starting with that compound. You can see that we need to add one extra carbon. The product has one extra carbon in that chain. So in order to add an extra carbon, we oxidize, and here we can distill the product so that what we get is an aldehyde. So we are oxidizing using potassium dichromate and concentrated sulfuric acid and distill. It changes that primary alcohol to aldehyde, and then we prepare the Grignard. We need to add one more carbon, so we start from, for example, bromomethane. To make the Grignard, we know that we should react that with magnesium in dry ether, add that to our aldehyde, and then H+, we end up with an alcohol that has one extra carbon. Now, what do we do to get to the product? The product is a ketone, not a secondary alcohol. So we just oxidize the secondary alcohol. Now we need to get a ketone. So we use potassium dichromate, concentrated sulfuric acid, and heat under reflux. Remember, to get an aldehyde, we distill, but to get a ketone or an acid, we heat under reflux. The second step of the industrial preparation of the raspberry ketone involves the reduction shown. So we are changing the side chain that has a double bond, and we are just changing it into a single bond. We use hydrogen in presence of a catalyst. We should know that usually the catalyst is nickel or platinum. Suggests why the choice of reducing agent is important in this reaction. Remember, we want a reducing agent that will reduce only the C double bond C, but not the ketone. We don't want to change the ketone to an alcohol. So we use hydrogen, presence of nickel, because it will react with the C double bond C, but will not affect the ketone. The alpha ionone and beta ionone molecules are structural isomers. Compare and contrast the stereoisomerism of these two molecules. On the structures, circle any features of the molecules that give rise to stereoisomerism. Okay, what kind of isomers do we have here? First of all, we have a double bond, and both of them have E isomers due to the presence of the double bond in that isomer. So both of them are E isomers, or what we call trans. Then, what kind of isomers do we also have? The alpha ionone has a chiral center, and that means it can also have optical isomerism. Identify with an asterisk the carbon atom environment in this compound, which would be expected to produce a peak with a quartet splitting pattern in a high resolution proton NMR. So where do we have a proton that will be a quartet? Of course, to be a quartet, that means the neighboring carbons have a total of 3 hydrogens. So where do we have that? If you look at this carbon, we have on one side 1 hydrogen and on the other side 2 hydrogens. So that proton on that carbon that we have an asterisk on would be a quartet. Predict the number of peaks in the carbon-13 NMR spectrum of this compound, which has the molecular formula C13H20O, and justify your answer. So how many different carbon environments do we have? If you look at this, all of them are different except for those 2 methyl groups on top. So this is a C13, but 2 of them are the same, so this will give 12 peaks for the carbon-13 NMR, since both methyl groups are equivalent. And that's the end of this paper. I hope this was useful to you, and Good luck on all your exams, and thank you for listening.